Hello class, welcome. This is Calculus 1, Math 2413, and I will be your instructor this semester. I am Oscar Villalobos, and let's get started, right? Let's go ahead and get started with section 2.1, right? And 2.1 on your calculus book, all right? It's going to be a preview of calculus, all right? What is to come, all right? What is expected of us? All right. So let's get started, right? So, right, and how this is going to work is I'm going to give a few examples of what is to be expected in, right, what's going to be coming up in the homeworks, right? What was the section about, right? So I highly recommend you read the book, you skim the book, all right? I don't expect you to be experts or understand everything that you read in the book, but at least want you to have an idea, right? Have your, you get your feet wet before attempting the homeworks, right? And things are going to be much more clear that way, right? So let's go ahead and get it started with example number 1. So for question number 1, right, they want you to approximate the areas under the curve below, right, from x equals 2 through x equals 6 using left endpoints, right, and 4 subdivisions, right? So all this means here, so let's go ahead and get a red marker. All right, so in other words, my focus is going to be between 2 and 6. My focus is between here and here. All right, they want me to have 4 subdivisions, right? So that means I'm going to have 4 rectangles, all right? So in other words, one rectangle is going to be from here to here, one rectangle is going to be from here to here, one from here to here, and one from here to here, all right? If it was 8, all right, if it was 8 subdivisions, right, you would have 8 triangles, right, with divisions here, 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 and here, all right? But more on that in the upcoming sections. But for now, right, you just this 4. And specifically here, they're asking me to find the area using left endpoints, right? Left endpoints, meaning you're going to start at the very far left of the value, right, from your initial value, and you're going to go all the way up. And when you hit that graph, you're going to go across and down to the right, back down, right? And you're going to do the same thing with the other division, right? With the other subdivision, you're going to go up all the way from here. And when you hit this, you're going to go over and then back down. You're going to do the same thing for all of these. You're going to go up, then down. You're going to do the same thing, up, across, and then down. Right, so that right there is 4 rectangles, right? 4 subdivisions. All right. Now I need to find the area of that, right? And we know how to find the area, right? Yeah, of a rectangle, right? That is what? Length times width, or length times height, right? Let's do that. Length times height. Base times height is, you can use that as well, right? Base times height. So for this first one, right, I'll call this value my first one. My base is 1, right? Because the difference between 2 and 3 is 1, or you can say, 3 minus 2, right? So that is going to be 1 times my height. My height is about, it's not 2.5, but it's slightly lower, so I'll say 2.4. Right? It's about approximately 2.4. So the area for that rectangle is 2.4. All right, let's go on to the second one. For the second one, right, again, my base is just 1, and my height is about not 3 exactly. You know what? I'll say 3. That's pretty close to 3. Right? It's a little bit under, but we'll guesstimate, right? There is going to be room for error. All right, so it doesn't have to be precise, but you have to be pretty close. My base is again 1, and this one, I would say this third rectangle, I would say that's not 3.5, so I'll say 3.4. That's 3.4. And last but not least, that is, what do we think? 3.8 maybe? Like about 3.8, right? say 1 times 3.8, right? This is 3.8, right? And I want to know the entire area under that, right? I want to know the entire area under that. So all I'm going to go ahead and do is add these up together, right? So my area is 3.8 plus 3.4 plus 3 plus 2.4. Right, and I get my value to be approximately 12.6 squared units. Right, in this class, you are going to have to write your units out. All right, you have to be precise. So this is approximately 12.6 squared units or units squared. All right, so let's go ahead and move on to the next example. All right, you're given a graph here, right? A curved graph, and then you're asked to find the slope of the secant line, right, through the point -1, through the point 1, -1, and 4, and f at 4. Okay. So one thing that I wanted us to go ahead and let's go ahead and close this. So some notation, right, is slope. We in our algebra courses, right, we associated this with what letter? M, right? Right, and we said, and one thing that I want us to know going in here, right, going into this, is that slope, right? If you're asked to find the slope of the secant line, same thing as finding that slope that we're used to finding, right? And I'm going to expand that definition even more. I'm going to go ahead and expand the definition even more. This slope is also the same thing as average rate of change. So in other words, if I ask you, hey, find me the average rate of change of this, it's just saying, hey, find me the slope. All right, that's all it's saying. All right. And last but not least, what is the formula for slope, right? What is the formula for slope? We know that is the difference of y over the difference in x, or more specifically, what we're used to seeing is y2 minus y1 over x2 minus x1, right? So in other words, you just need 2 points, all right? You can go ahead and find slope as long as you're given 2 points. All right, so I'll go ahead and save that here for later because that's going to be coming back. All right, go ahead and copy this because I'll be needing that later. So let's go ahead and find out what this means. Right, as a refresher, this is -1. F of -1, that just means whenever x is -1, your y is that value. So in other words, it wants you to find y whenever x equals -1. So let's go ahead and find that, right? We have our graph here. That is this point right there, right? That is going to be 3. So in other words, this is just 3. F of -1 is just 3. Right? I'm told another point whenever x is 4. Well, I can tell you what y is whenever x equals 4, right? Go to 4 down here. Well, that's just -1. So in other words, I would rewrite those to use points that we're used to seeing, right? And I know since I have 2 points, right? This is x, this is y, this is also x, this is also y. I don't want to get these confused, right? So I'm going to go ahead and label these 1, 1, and then these 2 and 2, right? And at this point, right, I can go ahead and find the slope of the secant line because I know that's just average rate of change, and I know that is just m, which is just slope, right? And I know the formula for slope, it is y2 minus y1 over x2 minus -1. Very nice. What I'm going to go ahead and do now is simplify. -4 over, what's that? 4 plus 1, which is -4 over 5. And that is the slope of my secant line. Okay. we got more here, right? So I'm told the following table shows the daily receipts in millions of dollars for the movie The Hunger Games after its opening on the 23rd of March, 2012. All right, and I'm giving all these values. And they want me to find the average rate of change from day 49, right? From day 49 to day 77, all right? So that is going to be, let's go ahead and see here. Where are they at? 49, right? And then 77. So in terms of a point, right? On day 49, the receipts in millions was 4.505, right? For day 77, that was 1.072, right? So again, right, they're asking here to find the average rate of change between those 2 days. Hey, we already know what average rate of change is. That's just slope of the secant line. That's just slope. That is just y2 minus y1. Right, that is y2. All right, let's go ahead and label these. All right, this is x1, this is y1 because that's for group 1. This is x2 and y2 for group 2. So this is 1.072 minus 4.505 all over 77 minus 49. All right. Let's go ahead and see what the numerator gives me. That ends up giving me 1.072 minus 4.5. That gives me negative 3.433 all over 28. And this is going to be 3.433 divided by 28. This here would be negative in once, we'll say 4 decimal places, right? So 0.1226. Okay. And since we want our units, the units on the top, right, was millions of dollars. Millions of dollars per, the one on the bottom was per day. So this is, in other words, millions of dollars for every 1 day. We said our units are important. Very nice. Okay, let's go to example number 4. All right, let's go to example number 4. For each value below, enter the correct number to 4 decimal places, right? Suppose an arrow is shot outward on the moon with a velocity of 62 meters per second, then its height in meters after t seconds is given by this function, right? H of t is equal to that. Find the average velocity over the given time intervals, right? So in other words, you're going to be giving 2 intervals, right? These intervals are going to be A and B. And B. And the formula, right, to find your average rate of change is going to be f of B minus f of A over B minus A. All right. And this again, right, this is just an extension of that formula, right? Similarly to the other problem that we were looking at, where we said that f of A just means I'm sorry, f of B just means the y that belongs to that B, right? So the same thing here. So in other words, all I'm really doing here is expanding this even more. So then this is just the same thing as f of B minus f of A all over B minus A. So again, right, you'll notice that with this class, we're going to be dealing just with a lot of slope. That's all we're really dealing with, right? Well, not all we're really dealing with, but for the most part, right? All right, so pretty much that's the formula I'm going to use, and I'm going to label and identify my A. Well, my A is going to be 5, and my B is going to be 6. All right. So one thing that you may want to do first is find f of B and f of A first, all right? That's generally right what I like to do first. So let's go ahead and find that. Let's go ahead and find f at a, right? All this means is that I'm going to plug in a, which is 5, into my given function. All right, my given function was h of t equals 62t minus 0.83 t squared, right? So that's all that means, right? All I'm going to plug in is going to be 5 in there. So this is going to be 62 times 5 minus 0.83 times 5 squared. All right, let's go ahead and plug all of that into the calculator and let's see what we get. Right, and I end up getting my f of a part is 289.25. Let's go ahead and find my f of b. F of b just means I'm going to go ahead and plug in b into that function, which is 6. So I'm still doing the same thing, but all I'm doing is plugging 6 in there. All right, let's see what that gives me. This gives me 342.12, right? Now that you have those, right, I'm going to go ahead and plug it into this formula, right? That slope formula, which is just f of b, which is 342.12 minus f of a, which is 289.25, all over b, which was what, 6, all right, minus 5. Let's see what this gives me. 342.12 minus, all right, this gives me divided by 1. My answer here would be 52.87. 52, right? And this is, I'm dealing with velocity here, right? So this is going to be meters per second. Units are important. Right? 52.87. Okay. Right, and you're going to be giving a list of these, right? You're going to go be giving a list of these. So you would do the same thing all over again, just for a different, A and B. All right. Okay, now this is going to be a little bit different now, right? This is going to be a little bit different now. Okay, and right now we're going to go ahead and get started on the instantaneous rate of change, right? The instantaneous rate of change. All right, and this is what we're going to be dealing with a lot in this class, all right? Finding the derivative of functions, all right? Finding the instantaneous rate of change, right? And you're going to go ahead and use what's known as the difference quotient, all right? My difference quotient is here. Very nice. So, right, so in other words, estimate the instantaneous rate of change of the given function h at that given x function. In other words, choose x values that are getting closer and closer to 1, and then compute the slope of the secant line at each of those values, right? So let's go ahead and find out how do we do this, all right? So how you start is, the first thing you're going to want to do is use this function, right? Use this formula. Right, and we're going to be focused on the top two. We're going to be focused on the top 2 parts. All right, I'm going to be focused on finding out what f of x plus h is. Right, all I'm doing there, right? All I'm doing there right now is I'm going to plug in x plus h. I'm going to treat that as one thing, and I'm going to plug it in inside my given function. All right. So in other words, I'm going to plug in x plus h into my h. All right. So this is going to be 2 times the thing I'm inserting, right, which is x plus h plus 4. Go ahead and go ahead and look at, go ahead and compare these two, right? That's all I did. And what I'm going to do now, what you're going to have to do for most of the time is simplify. In other words, you're going to have to distribute. You don't want any parentheses. All right, so I have here 2 times x plus h times h plus 4. Very nice. Now I'm going to go ahead and FOIL, all right, first. Outside. Inside. Last. Okay. What I'm going to go ahead and do now is distribute that 2. So this ends up giving me 2xh plus 2x squared plus 2xh plus 2hx plus 2h squared plus 4. All right. And one thing, right, that we know is that if you have A times B, this is the same thing as B times A. For example, 3 times 2 is the same thing as 2 times 3, all right? If they're multiplying, that order doesn't matter if you're just dealing with 2 terms like that. So in other words, I can rewrite this as 2x squared plus 2xh plus 2xh plus 2h squared plus 4. Right, and how many of those xh's do I have now, right? That means I now have 4 of those. Right? Whew. This is my f of x plus h. Right? This is my f of x plus h. Then I need to subtract that from f of x, but I know what's f of x. That's just the function that was given to me, which is h of x, right? And I know all over h. So now I have everything that I need, right? And now I have everything that I need. Let's go ahead and move this to the side. So in other words, what I'm trying to do here, all right, is going to be the limit, and I'll go ahead and I'll fill you all in on what that means. The limit as h approaches 0 of h of x plus h minus h of x all over h, right? Okay, so all I'm going to do here is the limit as h approaches 0 of h of x plus h. I simplify that, and this gave me 2x squared plus 4xh plus 2h squared plus 4 minus, right? Minus, and make sure you always use parentheses, right? Because that negative has to distribute to everything you have. Minus my h function. Well, I know this was just 2x squared plus 4 all over h, right? What we're going to go ahead and do now is just simplify the numerator, all right? And that's going to start, if you've already simplified this left side, which we already did, right? All you have to now focus in is distributing that negative value and then simplifying, and things should cancel out. If things don't cancel out, go ahead and check your work, right? So in other words, this is the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared plus 4 minus 2x squared minus 4 all over h. Okay, what can cancel out? Let's see, what can cancel out? These 4s can cancel out, right? What else? And these 2x squares. All right, those cancel out. Meaning, I'm left with the limit as x approaches 0 of 4xh plus 2h squared all over h. Ooh, so far so good. Very, very nice, right? Okay, what I'm going to want to go ahead and do now is, whenever you're doing these, right, whenever you're finding the instantaneous rate of change using the difference quotient, you want to go ahead, once you get it to this point where your terms cancel out, go ahead and factor the top. Just factor the top. Do not, in other words, specifically, I want you to factor out an h. Sometimes you may be able to factor 1 or 2 or none, depending, right? So I can factor out an h. More specifically, I can only factor 1h. So if I factor out an h from the top, I'm left with a 4x plus 2h all over h. And the reason I want you to factor first and then cancel out, it's because most of the points are taken off because things weren't canceled correctly in this spot right there, right? And I want you all to not get points taken off. So I want you to first factor and then cancel out. And yeah, I see here, right? This cancels out with that. So I'm left with the limit as h approaches 0 of 4x plus 2h. Right, once you get it to this part here, right, you take what's known as the limit. The limit just says, hey, I want you to plug in 0 for the h that you have. All right. So what happens as h gets very, 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 very close to 0? It's not 0 exactly, but it's approaching it. All right. Well, right. One way you can visualize it, it just becomes 0. So technically, what I have here is, after I take the limit, I have 4x plus 2 with an h as a 0, right? And doesn't matter how close I get to 0, right? 2 times anything by 0 or very close to 0, right? It's going to be 0. So I'm going to be left with 4x, right? I'm going to be left with 4x. And if you remember from our formula up here, the notation, right, after you take the limit is f of x, or in other words, I'm dealing with h, right? So it's not going to be f, it's going to be the derivative of h is equal to the answer you got here after you plugged in your limit, right? So in other words, that is my derivative. That is the derivative of my function, right? But if you look closely at the question, they didn't want the derivative at any point, right? Because if I were to ask you, hey, give me the instantaneous rate of change of this function h for any point, any point, this would be it, right? Because I didn't specify what x to give. But here the question does specify which x, right? So that means you're going to go ahead and plug in 1 for every x that you have, and that gives me 4, meaning that is the instantaneous rate of change for that given function whenever x equals 4, whenever x equals 1. This section is going to be section 2.2, the limit of a function. The limit of a function on your book is going to be on page 135, right? Going to be page 135. And, by now you should have already read that section, right? Skimmed that section to have an understanding of, what's going to be covered in this section, right? And we're going to be dealing with graphs and functions. Right? And whenever we're talking about limit of a function, we're going to be focused on an x value, right? On an x value. And this x value, we'll call it, right? It can be any number, right? So for simplicity, we'll call it a, right? We'll say a is the number that x is approaching, right? So there are 3 different steps, right? There are 3 different options, right? You have the limit as x approaches a from the left of a function, right? And when you see that negative on the top right of that number, right, it means from the left, right? So you're going to zone in on the x value that you're being asked to approach, but you're going to approach it from the left side, right? Slightly from the left. You are also going to be finding the limit of a function as x approaches a, but from the right, okay, from the right. And you're also going to be finding the limit of a function as x just approaches a, right? And as x approaches a, that means you're approaching it from the left and from the right. So you're like honing in your you're getting tighter and tighter and tighter from both sides, right, of that function. Right. One thing to remember, right? One thing to remember is to know if the limit as x approaches a from the left is equal to the limit as x approaches a from the right, then this means it is the same, that answer, right? If from the left is it's an answer, from the right it's from the same answer, then that means as x approaches a from both sides will be that same answer, right? Similarly, if you find out that the limit of x approaches a from the left does not equal, it is not the same as the limit as x approaches a from the right, then you can say that then the limit as x approaches a from both sides does not exist. Right? So it must be that same number, right? It has to be that same number. Right? And one thing to remember is the approaching limits from both sides is different from taking the function, from getting the function at a specific value, right? This is what we're used to seeing, right? If your x equals a, what is the y that is spit out, right? What is the y that is produced? So one thing to remember is this does not always equal this, okay? And we're going to go ahead and do a few examples, right? We're going to go ahead and do a few examples. Okay. All right, let's go ahead and apply this. So this here, we're going to start with example of 2.2.1. All right, you're given a function below, right? There's a function below, right? There's a graph, and you're asked to find the limit as x approaches -2 of that function. Okay. So one thing I know I have to do right from the start is find the limit as x approaches -2 from the left side. Right? From the left side, right? So in other words, you're going to go to -2, which is here, and I'm going to approach it from the left side, right? I'm going to approach it from this side, right? And I'm going to find out what y does it give me as I get close to that. It's 2, right? It's 2. So this is here is going to be 2. Right, now I'm going to go ahead and find the limit as x approaches -2, but from the right side, right? Well, if I'm approaching it from the right side, right, it's right here. I'm getting closer and closer to that. I'm forever getting closer. And hey, guess what? That is also 2. So since these two are identical, if I'm approaching it from the left and from the right, right, we said that the limit as it approaches x -2 from the left is equal to the limit as x approaches -2 from the right. And that must mean that that is equal to the limit as x approaches -2 from both sides, which is what? 2, right? You know that because these two were identical. All right. Go ahead and call this A. So my answer is 2. Right? And then, right, you're asked here to find f at -2. Right? That's the example I'm giving. What is whenever x equals exactly -2, it's not approaching, right? You're not getting tighter and tighter and tighter closer to it. It's exactly 2. What is it? Well, if it's exactly 2, right? I'm sorry, if it's exactly -2, then this y, right? This answer is just 2. Hey, very nice, right? So in this case, right, we see that this line is continuous, right? This is continuous. There are no jumps. There are no disruptions, right? We see that it's also 2, right? It is also 2. Okay, you have another example here. Oh, and it's not this. This is very similar to the one we found. We'll go ahead and do this one, 2.2.4. All right, 2.2.4. So I'm going to ask to find you're going to be asked to find the limits as x approaches -1. All right, this function f of x. All right, so we know first step is we need to approach this. We need to hone in on -1, but I'm going to approach it from the left first, right? I'm going to go ahead and approach it from the left of that function, all right? So, okay, I'm zooming in on -1, right? So -1 is right here, right? It's that vertical line. But I want to approach that from the left, right? From the left. So that means I'm going to be focused on this line here, right? I'm going to be focused on that line. And as this gets very, very close to -1 from the left, right? It's getting closer and closer. What does it get close to? What y is that? -1, right? That's going to be -1. Now we're going to do the same thing, right? We're going to zone in on -1, but from the right, right? So again, here, this is still -1, but I'm going to find a line that exists on the right side. All right, it wouldn't be anywhere here because there isn't a line there that I can approach it from the right, but there is up here, right? There is up here. I'm getting closer and closer and closer to this, and what y is that? What y is that? Let's go ahead and change the markers. What y is that? Y is 3. Ah, right. We see here that as I approach it from the left, it is -1, and that as I approach it from the right is 3. These are not the same, right? These are not the same, right? And we said that if the limit as x approaches -1 from the left does not equal the limit as x approaches -1 from the right, then the limit as x approaches -1 from both sides, right? Because it's a contradiction. You're telling me, hey, from the left is equal to -1, but from the right is equal to 3. It has to be the same thing, or else it contradicts itself, right? It cannot be two things at once. Therefore, this does not exist. Right? Therefore, this does not exist. Right? For B, I'm going to ask you then to find what is y whenever x is -1. So in other words, you're looking for a solid answer. It cannot be an open circle. It has to be a solid answer. All right? So it cannot be this, right? Because that's an open circle. It cannot be the one on the bottom. That's an open circle. Hey, it has to be this one in the middle. All right? Whenever x is exactly -1, what is y? It's 1, right? It's 1. Right? And we see here, right, how all these three answers differ, all right? All these three answers differ. 4 answers, right? Because approaching it from the left, approaching it from the right, approaching it from both sides, and evaluating that function at that specific x. All right, let's go ahead and do another example. Go ahead and make this a little bit bigger for you guys. Right there. All right, we have another one. All right, I'm going to ask you find the limit as x approaches, what is this? 2. All right. It doesn't have a negative or positive, so I know I have to split this into 2 parts. The limit as x approaches 2, of this function. More specific. Function, but from the left. All right, so I'm going to locate x equals 2. And I'm going to look for a line that approaches, that exists on the left side. Which right here. Right, there's a line right there. It's going forever this way. As I get closer to that x, as I get closer to this x equals 2, what is the y that is produced? Right, that I would say -3. And you might say, hey, but there's an open circle there. Remember, I'm not asking for the function at a specific value. I just want to know what happens when I get very, very close to it. All right, when I get very, very, very close to it, right? So whenever my x is 1.9 or 1.999 or 1.9999999, all right? So okay, it approaches -3. I'm going to go ahead and do the same thing. All right, I'm going to say the limit as x approaches 2, but from the right of that function. And similarly, to the right of that function, there's a line here, and I get closer, 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 closer. I can get forever close, right? And that is also going to be -3. right? Sure, there may be a hole there, but I'm not asking to find a function at a specific value. I just want to know what happens if I get extremely close to it, right? What am I forever getting close to? So this means that if the limit from the left equals the limit from the right, then it must mean that the limit approaches -3, right? And for B, right? For B, I'm going to ask, what is the function at exactly 2? All right. All right, and we see here, right? We see here that that there's a hole here, right? Nothing is defined there, but there is a value up there, all right? And that means whenever x is 2, what is y? 2, all right? It's just 1 and 1. There's no approaching. It's exactly 2. I want to know why when x is exactly 2. All right, and like again, right? Like I said, just because the limit of this one existed does not mean that that this one is going to, that these two are the same value. All right. Right, and that assumption cannot be made because this is not continuous, right? This isn't a continuous function, right? It's continuous here, 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 here. Ooh, and then something happens there, right? This was there's a hole there, right? This is not a continuous function. This is discontinuous, right? It was continuous up to here, but then there's a hole removed. All right, there was a hole removed from there. All right, so this is why these two, where to go? Right, this is why they do not equal each other, because it's not completely smooth. Okay, let's go ahead and move on to our next example. All right, we're going to go ahead and be dealing now with finding limits, and specifically with sine functions. Right, specifically with a sine function. All right, and if you look on your book, where I just have this page here for you guys, where it shows the proof, right? Where it shows the proof, where it shows why exactly, right? I will go ahead and leave that as an exercise for you all. We are told here that, just have to take me a second. There we go. Right, this is going to be on page 171. Right, this is going to be on 171, right? Example 2.24, right? And it's going to continue on to the back, right? Onto example 2.25. All right. One thing I want you to know is this identity. All right. The limit as x or any variable, right, as it approaches 0, it has to be 0. All right, that x must approach 0 of, let's just say, sine of x over x. That's always going to be 1, right? That's going to be 1. So let's go ahead and see here, right? Let's go ahead and see here as a demonstration so we can have a visual of exactly what's going on, right? I'm going to go ahead and pull up Desmos, right? And if you're not familiar with Desmos, it's a great calculator, all right? It's a great calculator. So this is what sine of x over x looks like, all right? And since they were asking me to find the limit as x approaches 0, right? So that means I would have to approach it from the left and from the right, all right? I would have to approach x equals 0 from the left and from the right. I know that if I'm approaching it from the left, I get close to this value here. And if I approach 0 from the right, I get exactly that value there. Therefore, meaning, right, that if I approach it from the left and it's 1, and if I approach it from the right, it's 1, then, you know, that limit is 1. Right? So that's the identity I want us to remember, right? To go ahead and notate. Moreover, right? Moreover, if you have the limit as x approaches 0 of sine of any number, right? So let's just say any positive number, all right? Any number greater than 1, right? Any integer greater than 1, say 13, right? 13x, right? And in other words, if that 13x inside the sign is the same number in the denominator, then it's still going to be 1, right? It's still going to be 1. So let's just say I would say in here, the limit, and I'll go ahead and change it up a bit here. I'm not going to use x. I'm going to use theta,
It doesn't matter, right? As theta approaches 0, sine of, let's just say 15x, I'm sorry, 15 theta over 15 theta. Hey, it follows this formula here, right? Those two ends are the same. Therefore, you would just have to know that that equals 1, right? And I'm not going to ask you to prove it, all right, or to graph it, all right? You're not going to be asked to do that. So, right, let's just say you were here and we went ahead and changed this to 15, right? This is the graph now that you have, right? This is for 15x. But again, notice, if you approach 0, if you approach 0 from the left, and you approach 0 from the right, what is that value? 1, all right? So, right, and you can say, hey, can I put 100 in there? Yeah, you can put 100 in here, right? And again, what happens? It is still 1, right? So as long as those numbers match, right, you can have 63, right? As long as those numbers match and you have a variable at the bottom, right? 63x in the inside of sign and at the bottom, it's always going to be that. So that's something, I mean, and I'm giving you all a hint, right? That's something that's going to be showing up, right? And this is why I said here, moreover, right? Moreover, not more oven, moreover, all right? If you see that pattern. If you don't see that pattern, right, then we'll see, what do you do when that happens, right? Well, what do you do when that happens? Exactly, right? I have an example here. Evaluate, estimate the limit numerically, or state that the limit does not exist. All right. Okay, so we have the limit as x approaches 0 of sine of 13x over x. Oh man. Okay. What ends up happening here, right? It's not balanced, right? This here isn't balanced. So what do we have to do? We have one. I need to go ahead and I know that if it was the same values, these two would disappear, all right? That they would go ahead and just cancel each other. That inside part would equal 1, all right? So what I'm going to go ahead and do is, you can add a 13x at the bottom. In other words, you can multiply the bottom by 13. You just have to be sure that you do the same thing to the top. You need to keep things balanced, all right? Whatever you do to the bottom, you need to do to the top. So in other words, this is now the limit as x approaches 0 of 13 times 13x over 13x. All right. Moreover, right? One thing I can do is focus on just this limit as x approaches 0 of 13 times sine of 13x over 13x, and have two things being multiplied each other, right? This is 13, and I have this entire piece, all right? And in your book, if you look for your limit laws, right, your limit laws are going to be on page 161, right? Theorem 2.5, your limit laws, right? This, if you look at the constant multiple law for limits, right? This just means if two things are multiplying, all right? So if two things are multiplying, you can apply that limit. In other words, you can distribute that limit to what you're focused on, right? So in other words, this is limit as x approaches 0 of 13 times the limit as x approaches 0 of sine of 13x over 13x. Right? One thing you'll know that is, it should be here. If you look on page theorem 2.4, the basic limit results, right? When you're dealing with constants, right? What constants are just numbers without variables, right? Specifically here. Since there's no x for you to plug in, it's going to be that, right? So in other words, your answer for this one is just going to be 13, right? And on the one on the right, whenever you apply your limit, hey, this is an identity. Right? We looked at this before. These are the sign ones I was talking about. So the first one is, it's just going to be, we said that is 1, right? So then I just multiply those two together. 13 times 1 would just give me 13. And that right there is my answer. right? So the key thing here was to make sure there was a 13x over a 13x. If it wasn't, I would go ahead and apply it, but just keep things balanced. All right. We're going to be dealing with limits and specifically looking at piecewise functions, right? And remember from college, we've probably seen these in college algebra, right? And pre-cal, right? Limits, right? Limits. So what I want us to find here is to find the limits as x approaches 5 of this function, right? That's what you're asked to find. So I know I can break this into 2 parts. I'm going to find the limit as x approaches 5, but from the left, right? And remember from piecewise functions, right? This one is saying you're able to use this one if you're less than or equal to 5, right? So in other words, anything from the left is going to be that, and anything greater than 5, that's on the right side, right? That's going to exist on the right-hand side, all right? So what that means is I'm going to plug in 5 into that top function, right? So I'm going to go ahead and plug in 5 into that top function, and so let's see what that gives me, because that graph should only exist on the left-hand side, all right? So this is 2 minus 5 minus 5 squared, which gives me 2 minus 5 minus 25, which is what, negative 3 minus 25, which equals, right, which equals negative 28. Okay, very nice. So now I'm going to go ahead and take this limit from the right-hand side, right? As x approaches right, but 5, but from the right. And I know, right, again, right, whenever I was dealing with these piecewise function states, that at x equals 5, a certain graph exists, and on the right, a certain graph exists. They do not cross over, all right? So that just means I'm going to go ahead and plug in 5 but into the bottom function, right? I'm going to go ahead and plug in 5 into here. Minus 5, this is 10 minus 5, which is equal to 5. Now you'll ask yourself, are these two the same thing? No, they're not, right? They're not. So this means that the limit as x approaches 5 from both sides does not exist. Does not exist. And remember, you have to show all your work, all right? For those who are watching, you have to show all this work. If you submit your homework assignments and there's no work, right, you need to justify your answer. If there's no work, there's going to be no credit, all right? So you need to show all these steps, right, of why. You need to justify your answer. Okay, we're going to go ahead and do more limit laws, right? We're going to go ahead and do evaluating the limits, all right? So here we're given a function. We're not given a graph no more, right? 4x minus 5, right? And again, let's go ahead and to turn over to page 161 and make sure you know these limit laws, right? Make sure you know these rules, right? So specifically here, this one, I'm going to want to go ahead and use the sum law for limits, right? Which is the first one, right? Which states that if you're taking the limits of let's just say, polynomial, you can take the limit of each individual piece, right? And sometimes it's easier to do that, right? The limit as x approaches 1 of the first one plus the limit as x approaches 1 of the second one, all right? I'm going to go ahead and focus on this part here, right? All I'm going to do there is plug in that limit, right? That's all I'm going to do right now, plug in that limit. So all I'm going to do is plug in 1 into there. So this is just 4 times 1, which is 4. Okay, very nice. There was a plus here, so I'm going to go ahead and bring that down all the way down. Right, and this is a constant, right, from theorem 2.4, meaning that if you're taking the limit of a constant, the answer is just that constant, right? So this is just going to be negative 5. Why? Because is there an x for me to plug in? No, there isn't, right? So in other words, this is just going to be 4 minus 5, which is -1. All right. You might be asking, hey, can I just plug it into the entire polynomial? Yes, right? Sometimes it's going to be easier to take this route. Sometimes it's going to be easier to take the top part. How do you know? The more practice we have, the better, all right? Because remember, one thing I want us to remember, to do great in the exam, you have to watch the lectures, right? These video lectures, which are going to prepare you for the homeworks. The homeworks are then going to prepare you for the review, and the review is going to prepare you for the exams. All right. So you follow that pattern, right? You show all your work, you submit things on time, you're gonna do great, right? You're gonna do great. So, in other words, right, an alternate option would be, hey, can I just apply 1 into there? Like, yeah, let's see what happens. So you applied the limit, so now you get 4 times 1 minus 5. It's 4 minus 5, which is -1. Right, it gives me the same answer. Okay. Okay. So evaluate the following limits. Right, we're going to go ahead and evaluate the following limits for 2.2.16. Right. One thing that I want us to mention here, all right. In our previous classes, we were used to we would state if you're dividing by exactly 0, it does not exist, all right. But we can be more specific in this class, all right. We're going to go ahead and borrow from that. If you're dividing, but for example, right, my first example is going to be, let's just say you're dividing by a positive, very, 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 very small positive number. So let's just say you're dividing 5. Let's go ahead and get our calculator. Let's do that instead, right? So if you do 5 divided by a really small number, let's just say 0.05, right? It's going to give you a large value, right? If you do 5 divided by something even smaller, right? There's a trend going on here, right? All right, there's going to give you an even larger number. So if you're dividing 5 by a number that's very, very, very close to 0, but it's positive, right? It's positive. It's positive. Right, and you might be saying, hey, why did you write 0? That's just me representing a very, very, very small number, right? So if you're dividing any number by a positively small number, this leads to infinity. I need us to remember that, right? Another example would be, you can have 13 divided by a very, very, very tiny, small positive number. This is 15. I'm sorry, this is infinity, all right? So in other words, if you have a number divided by something very, 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 very small, this is going to be infinity. And we're going to be using this idea going forward in class, right? We're going to be using this idea. Similarly, if you have a number that's being divided by a very, very, very small but negative number, all right, what do you think this is going to be? Negative infinity, all right? If you had something again like this, also here, right? And this would also be negative infinity, all right? I'm going to go ahead and mention something else too, right? If you plug in your calculator, right, let's just say 3 divided by, let's use 4. 4 divided by a very, 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 very large number, right? And you can try this on your calculator. You can do 4 divided by 99, right? It gives you a small number. You do 4 divided by 9,999, it gives you an even smaller number, right? So in other words, if you have 4 and you're dividing that by infinity, by a very, very, very large number, this is going to tend to 0, right? And I need us to remember that whenever you have a number divided by infinity, all right, this would give me 0, right? That's going to approach 0, all right? And I need us to remember that, because it's going to be very, very important for these concepts moving forward, right? So here, right, I have negative, right, I'm going to go ahead and plug in negative 4x into, right, into there. All right, so let's go ahead and see what happens if I plug in a 2, but from the right-hand side, right? So my main focus is going to be on the denominator, right? So negative 4, and as a concept, so we can visually see what's going on, I'm going to say I'm going to apply 2, but slightly from the right. Right? I'm going to go ahead and plug in 2, but slightly from the right. So, right, and that can be 2.1, or if you want to be even more closer specific, you're plugging in 2.00000, I don't know, 1, right? You can see it like that. Or you don't want to use too many zeros, right? You get the idea. You may do something like that. Right? You're approaching 0, you're approaching 2, but from the right. Right, so that's what I'm notating here by 2 from the right-hand side, divided by 2 from the right-hand side minus 2 to the 7th. Okay, and I want us to think here for a little bit, all right? You have 2, which is slightly larger than 2, minus 2, minus a regular 2. What's left over? Is that going to be positive or negative? It's going to be positive, right? So 2 slightly positive minus 2, right? And to visualize it, you can do something like 2.1 minus 2, right? That's going to be positive 0.1, all right? You can use 2.000001. So in other words, the remainder there, right, is going to be a very, very, very small number, but slightly to the right. It's just positive. The 7th power, all right. Right on the top, you're right on the top. I'm just gonna leave it like that, right? I'm going to leave that like that, all right. That's just going to be right negative 4 times positive 2, all right. Because remember here, whenever you're doing these, you're not worried about the actual numbers. You're worried about whether it's a 0, whether it's not a 0, and it's more specifically about the sign. The sign is what matters. All right, but that's the most important part here. On the top, you have a negative number multiplied by a positive number. What's going to be on top? A negative number, all right? So let's just say, I don't know, negative 1, right? For example, just a negative number, right? A negative number. Divided by, you have something very, 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 very small that's slightly positive to the 7th power. That's still going to be pretty small, right? That's still going to be pretty small. And what we said earlier, right, that if you have a number divided by something very, very small, right, that's close to 0, that's just going to be infinity, right? So I know this is going to be infinity, right? But just look at this, right? We're still using concepts from algebra. You have a negative number divided by a positive number. So what's that going to give me? A negative number, all right? Another way you can do this, right, is just, you can just carry that all the way. You can just say negative 4 times a 2 slightly from the right divided by 0, right, a number slightly positive than 0 from the right. That's to the 7th power. That's just this. And it doesn't matter. The top are just numbers, right? That's going to be like what, 4 point something something something. I'm not worried about that actual number. I'm worried about the sign, all right? So that's going to be a negative number, right, divided by something very, very, very small. I know that a negative divided by a positive, it's negative, and it's a negative number divided by 0 from the slightly from the right. So I know this is going to be negative infinity, all right? And you may want to do, you take your steps with these, all right? Take your time with these, all right? Like I said, you have to show your work. Take your time with these. Right, to understand this, we're going to go ahead and apply the same concept here, right? Limit as x approaches 2, but from the left. So in other words, from the left of 2, this is like saying 1.99999, right? Or just 1.9, all right? Depending what you want to use to visualize it, all right? Negative 4, negative 4x over, oh, it's the same thing, right? X minus 2 to the 7th power. So I'm going to go ahead and plug that in, right? Like I said, technically in the top, you just have -4 times a +2, but it's slightly from the left, right? What was that? Right. This here ends up giving me, I have 2 slightly from the left minus 2 to the 7th. Right, and this is the important part, all right, is that bottom number going to be positive or negative, all right? Well, you have, right, you could go ahead and put it in your calculator real quick, right? Just choose something that's slightly less than 2, all right? Well, you could see 1.9 minus 2. What's that going to give you? That's a negative number, right? That's going to be a negative number. So in other words, I'm going to say this is -4, 2 slightly from the left of a very, very small number, but it's negative, right? To the 7th power, right? Slightly negative to the 7th power. And here's one thing I want to go ahead and focus on is we know from our college algebra courses, right, as a refresher, right, a negative value to an even power, right? Let's just say like x to the negative x to the 4th. This is always going to be positive, all right? That's always going to be positive. And negative x, right, or any negative number raised to an odd, that's always going to be negative x to that odd value, all right? So what I want us to see here is what happens to the negatives whenever there's an exponent on the outside, all right? So you have a negative number, which is very small, but I'll still consider it a negative number, raised to the 7th power. Is that become positive or negative? That is just, it stays negative, right? So it's going to be a negative number. All right, divided by -4, 2 but slightly from the left, right? And here, right, you have a negative number divided by a negative number. That's going to give me what? A positive number, right? A positive number. And we know any number divided by something infinitely small is going to be positive. It's just going to be infinity, right? It's just going to be infinity. So I want to go ahead and show you all what was it that we just did. All right, well, what was that we just did? All right. Let me go ahead and plug in this function here. If I remember correctly, it's -4x divided by x minus 2 to the 7th. Right, and I'm going to create an asymptote, right? An asymptote at x equals 2, right? And as a refresher, if you forgot what an asymptote was, I would go ahead and all right, remember the refresher, you get your denominator and you equal it to 0, and that gives you your asymptote. All right. Right, so the orange graph, let's do blue. The blue one is going to be my function, and the dotted line is my asymptote, right? So what we were finding here is what happens as you approach, 2, but from the left? Well, this arrow gets very, very, right? That arrow starts approaching 2, but from the left, and if you notice, that gets very, very close to it. But what happens? Is that arrow in terms of y, is it pointing upward or is it pointing downward? Right? If you're approaching it from the left, it's going upward. So in other words, that's positive infinity. That's going towards positive infinity. Right? And if you're approaching 2, but from the right, where's this arrow going? That's arrow going downward, right? And downward in terms of y is negative infinity, right? And if you notice, that's what we have here. As you approached it from the right, it was negative infinity. As you approached it from the left, it was positive infinity, all right? So in other words, if you're approaching the limits from both sides, it should give me the same thing, all right? If the left is equal to the right, it should be the same thing, but it doesn't, right? Because do these two match? No, they don't, meaning that this limit
does not exist. Right? That limit does not exist. All right. Like I said, I'm not going to you're not going to be required to use to use graphing utilities, or a calculator, but you're expected to know this, right? Because again, this is a refresher from our college algebra. If you have an absolute value on the top, right, a rational absolute value, right, you can go ahead and split this up, right? You can go ahead and split this up, right? The absolute value of 2x minus 8 divided by 4 minus x, right? This is just this. I want you to split this up into two parts. The top part, right, it's going to make the absolute value disappear, but I need you to put a negative in front of everything, right? Right, because this is a piecewise function now. This is a piecewise function. And on the top here, right, for your x boundary, you're going to say x is less than 4. Right, and for the bottom part, you're going to just apply a positive number in the front, or just a positive sign, right? But a positive sign just keeps everything the same for x greater than 4. All right, so this means if you want to look at it from the left of 4, this here is the limit as x approaches x from the left. All right, meaning you're going to go ahead and plug in 4 to that top function and see what it gives you. Right, so in other words, go ahead and write it here. The limit as x, we'll say a, right? The limit as x approaches x from the 4 from the right, from the left, of negative 2x minus 8, right? Oh, well, as it approaches that down what was given to us, 4 minus x. This is the same thing as finding the limit as x approaches 4 from the left of negative 2x minus 8 divided by 4 minus x, right? And all I'm going to do there, just very similar to the piecewise function that we did earlier, I'm just going to go ahead and plug that in, right? I'm going to go ahead and plug that into my function, and I'm going to see what it gives me, right? I'll go ahead and let you show your work for this, right? I would need you to show your work, but you'll find out that this gives me 2, right? This gives me positive 2. If you were to go ahead and plug it into the right-hand side now, right, to the bottom function, right, which would be not negative, right? It's going to be, well, it's the same function here, right, the original one, but I need you to split this up whenever you're dealing with absolute values, right? You need to show this work. This is going to be the limits as x approaches 4, but from the right, of 2x minus 8 over 4 minus x, right? And I'll let you show all your work, and this is negative 2. Right, meaning then as the x approaches 2 from both sides does not exist, right? Because these two are not even, right? They're not equal. I'm sorry, they're not equal, right? And let's go see, right? Like, oh, what does that function? What does that look like, right? If I were to graph this, right? This is, we said 2x minus 8 divided by, what was it, 4 minus x. So I see here, right? We see here that as that I'm approaching 4 from the left, right, it gets close to 2. But as I'm approaching 4 from the right, it approaches negative 2. All right, this approaches negative 2. Very, very nice. Okay, right now let's go ahead and jump onto the next section, which is going to be section 2.3. That's great. Let's go ahead and get started in 2.3. Let me go ahead and clear this up. All right. So again, we're going to be dealing with more limits, all right, with more limit laws, all right, and a few things I wanted to mention, right. Whenever you're finding these limit laws, right, for
for the most part, for this section, you're not going to be asked to approach from the left or from the right. It's just going to be, hey, I want you to plug this in. I want you to plug in this number into this function and tell me, is it a number? Is it 0? Is it infinity? Does it not exist, right? So the first thing you should always do with these is plug it in, right? Plug it in. If it gives you a number, that's fine, right? If the answer is 4, that's great. The answer is 4. If the answer is 0, right? 0 is a valid answer. That's okay, right? 0 is a valid answer. That's okay, right? So if you get 0, that's totally fine. There's no problem there, right? The problem is going to be when you're dealing with rational equations, right? Or fractions, and you get 0 over 0, right? That's going to be a no-no, right? That's going to be a no-no. This is what we're going to be looking out for, right? In this section. What happens if it's 0 over 0? All right. Just as a quick reminder, we said if you had any number divided by infinity, right? This is just 0. All right. And remember, you got to look at the signs too, right? There's variations to that, right? And the other way around, right? That if you're dealing with a number divided by an infinitely small number, right? By a very, very small number or something like 0, this is just infinity. All right. This is just infinity. All right. And we know, right? If you have, right, something like 0 divided by 3, right? This is just 0. All right, so these are like 3 things we should know, right? This one's implied from college algebra, right? From all of your previous courses. These 2 are new ones that we're applying in this class now, right? And then we said there's variations with those depending on whether, right, what's the signs at the top and the bottom. If they're both positive, right, a positive divided by positive, that's a positive. If they're both negative, it's going to be positive. If one is positive and one is negative, then we know it's going to be negative. So, all right, so this is what we're going to be focused on today. All right, and of course, right, and if at any point you have any questions, please use the discussion board, right? Please go ahead and use the discussion board, or send me an email, all right? Send me an email, ask me a question, all right? I'll be more than happy to help, all right? All right, so we have the first one, right, which is a refresher because we've seen something like this before, all right? We've seen it on the, as a previous example. So you're asked to evaluate this limit, right? You're asked to evaluate the given function, right? Your function is 5y to the 4th minus 4y, right? At y equals -3. Right? There are different things we can do here, right? You can plug it all in at once, or you can go ahead and separate these, right? So I know this is the same thing as the limit as y approaches -3 of 5y to the 4th. Plus the limit as y approaches -3 of -4y, right? Moreover, that 5, right, looking at this first one, the 5 and the y to the 4th is multiplying each other, right? I can go ahead and apply a limit law. So this is the limit as y approaches -3 of 5. Go ahead and put this in parentheses, times the limit as y approaches -3 of y to the 4th, plus, and right, and I have the same thing on the right hand side, the limit as y approaches -3 at -4 times, all right, that again, a product property, the limit as y approaches sorry, as y approaches -3, but of y. All right, all you're really doing here is distributing, right? You can see it as distributing the limit. Let's do the first one. The limit of a coefficient is just going to be that, right? It's going to be that constant. So this is going to be just 5, right? There's no y for me to plug in. For this other one, times, I'm going to plug in -3 for every y that I see. So in other words, this is going to be -y to the 3rd, or -y to the 3rd, plus, again, we got, right, I can just plug in it's just a constant, right? That is just going to be -4. And then the other one, I'm plugging in, I'm timesing it by every y becomes -3. I have that. All right. Oh, I'm sorry. This first one here should have been What did I do here? What? This is negative 3 to the 4th. I'm sorry. Negative 2 to the 4th. All right. So this one's going to be 5 times. Well, we know it's a negative to the 4th power, right? A negative, we said a negative value raised to an even. It's just going to be positive, right? So then we can just focus on what is 4, what is 3 to the 4th power. And this gives me 81, right? Plus, we have negative 4 times negative 3. Negative times a negative equals a positive, and 4 times 3 is just 12, right? And when we do 5 times 81, right, plus 12, I get 417. Right. So if I'm asking you to apply each limit law, right, you may end up getting an exam question like that, right, where I ask you, hey, apply, right, evaluate the limit, right? You can go ahead and take this route, which is very good because that's just extra practice for what's coming up. Or you can just apply negative 3 to the entire function in the top, right, which is just 5 to the negative 3 to the 4th power minus 4 times negative 3. All right, plug it in. You'd see it give you the same answer. So these are great laws, right? These are great limit laws. All right. Hint, right? Hint. I give hints for those watching the videos of what's to come, right? What can you do? Whenever you're dealing with these rational equations and you're taking limits, right? We said the first thing you're going to do is plug it in. Just plug it in. Right? And if it spits out an answer that you like, that's great. If it spits out 0 over 0, we're going to have to do something, right? So let me go ahead and plug this in. This is going to be, I take the limit, so this is going to be 2 to the 3rd minus 8 over 2 minus 2. This is 8 minus 8 over 2 minus 2, which is 0 over 0. Alert, right? Alert. It just means I have to do something here. All right, 0 over 0. I need to do something. The first thing you want to do, right, your first step whenever you're doing these limits, when you're evaluating these limits and you get a 0 over 0, factor. I want you to factor these, all right? Right, I want you to factor these. The first thing you're going to go ahead and do is find out how can I factor this? How can I factor this? Right, and as you may have already seen, x cubed minus 8, that has a form a cubed minus b cubed, right? And these are your, right, you're solving how to, you're learning how to factor these cubic functions, right? And there's also a cubed plus b cubed, right? And something like this is, you'll see something like this on your exam. Right, we said that you would have to go ahead and rewrite, right, from our college algebra previous courses. We find out that you need to write things, find your a, find your b, and once you find that, right, you can just go ahead and plug it into your formula. All right, so this here would be a minus b times a squared plus ab. Remember, not 2ab, right, because that's usually a common confusion. All right. For the bottom one, right, it'll be a plus b times a squared minus ab plus b squared. So make sure you memorize these. Make sure you go ahead and memorize these. Okay, so that means I want to go ahead and rewrite the numerator, right? Focusing on just my numerator here, I got x cubed minus 8, all right? You need to rewrite them in terms of something to the 3rd power, right? We know that 8, right? How can I rewrite 8 with something to the 3rd power? Well, that's just 2 to the 3rd power, right? Meaning your a is just going to be x, and your b is going to be 2. Do not bring in that negative, right? It's always going to be, your b is always going to be a positive value, all right? Do not bring in that negative. Meaning, this is a cubed minus b cubed, so I'm going to use the top one. It has to be the top one, right? And you already know your a and your b, so you just plug it in. And you'd find out, right, that you should get you'd find out, right, when you do your, right, when you plug all that in and simplify, you should get x minus 2 times x plus x squared plus 2x plus 4. Right. So, right. So now I rewrote the top, so I'm going to go ahead and divide it by my original denominator. Hey, and this is exactly why we're factoring, right? This is exactly why we're factoring. We want things to cancel out. I want things to cancel out from the top and from the bottom. Meaning, yes, these two cancel out, meaning that once you factor and cancel out, right, you're going to rewrite what you now have. And you apply the limit again. Take the limit again, and let's see what happens. Right? What does it give me? Do I get 0 over 0? Does it give me infinity, undefined? Right? So this is 2 squared plus 2 times 2 plus 4. This gives me 4 plus 4 plus 4, which is right. I just have 3 4s, which is just 12. Okay. So the limit of that function for x equals 2, sure, at the beginning you give me 0 over 0, but I went ahead and moved things around, right? And it gave me 12. And this is why we do that, right? Okay. Okay. So I'm going to go ahead and take these limits, right? Again, this is like the absolute value that we saw in the previous section. Right, we have 9x plus 1 if x is less than 9, cx if x is greater than 9, right? So I'm going to find out what it gives me whenever I go to the left, all right? Let's go ahead and plug that in. All right, so as I go from the left, you're going to plug in 9 to the top one, right? And I'll go ahead and let us know what it gives me, right? So you go ahead and plug in 9 onto that top one, and you should get 80, what is it, 82? 9 times 9, right? You got to show your work, 82. You may be asking, hey, for the bottom one, all right, there's a C. Is that an error? No, it's not an error. It's just an unknown number, all right? It's an unknown number, right? And when you plug it in there, all right, when you plug it in there, it gives me something C times 9, all right? Something C times 9, all right? So if the bottom one has an unknown variable, but the top is an exact value, right? We said that if the one from the left is equal to the one on the right, then it means that the limit from both sides does exist. All right, it does exist. Meaning, right, and for this next part, they're asking me, hey, I'm just letting you all know that the limit from both sides exists. Oh, what happens right here? Right, the limit from it exists, right? So what is that limit? What is the limit? Well, you can either say it's C9 or it's 82. But C, I don't know what C is, and that's fine. So you're going to know the one that you know the answer for. It's 82. My answer has to be 82, right? My answer has to be 82. All right, and if you're asked, hey, find C, sometimes you may have A, right? Sometimes you may have A or B, all right? What do you do there, right? So whenever you're trying to solve for this variable in there, right, like for that C, what you do is you get the top one, 9x plus 1, and you equal it to the bottom one, right? Because in other words, you want to combine. The reason you do that is, let's just say one graph is doing this, right? But let's say the bottom one, it can go from here to here, or you can go from here to here, or you can go from here to here. It can be any of those, right? It can be any of those, but you want it to be stamped. You want it to connect at this point exactly, right? Because if it's that point exactly, this is continuous, right? It'll be continuous. So that is why you equal them to one another. Because if you equal it to one another, it's gonna force it to start here, right? It's gonna force it to start there. All right. So That is y equaling to one another. I don't know what c is, that's fine, but I know what x they should have in common, right? I know what x they should have in common. This is x equals 9, right? It's always going to be that value there, right? So that means for every x that I have, I'm going to plug in 9. Right? And what do you think we do now? We solve for c, right? We solve for c. You go ahead and divide both sides by 9, meaning c must be 82 over 9 for this piecewise function to be continuous, right? For the limit to exist on both sides, all right? Okay, we have another problem, right? We have, what is this? 11, right? You're asked to evaluate the limit, right? So I'm going to go ahead and plug in -2 into all of there, and if it spits something out nice, hey, that's great, right? That's great. And remember, you gotta make sure the top and the bottom equals 0, right? You cannot assume, hey, it's equal at the bottom, so it has to be 0. Because sometimes you're right, they might pull a fast one on you, right? I might pull that's not a fast one, right? But I just want to make sure that we're not skipping any steps, that we're taking things by order. The top is +4 minus 8 over 0. This is 0 over 0. I got to do something, right? And that's fine, right? So, right, whenever you're doing these, you have to show your work. You need to show this. I need you to show that, right? You need to show your work. Meaning, okay, we said that whenever we have these, then the next step would be to factor, right? Can I factor anything at the bottom? No, I cannot factor anything at the bottom. What about the top? Yes, right? That's a trinomial, right? And there are different ways you can do this, right? And as a refresher, you may want to look up the AC method. You may want to go ahead and look up the AC method. Right? You can YouTube it, right? There's a lot of great YouTubers out there. But as a refresher, right, the AC method states, I'm going to multiply the first number and the last number. And the first number here is 1. The last number is -8, right? So this is plus multiplication. This is going to be addition. Right? This is AC. This is going to be B. Right? Multiplying A and C, this gives me -8. B is just going to be that middle value, which is -2, right? And the game is, you're looking for two numbers that multiply to give you -8, but whenever you add those two same numbers, they give you -2. All right, and you'd find out that those numbers are 4 and +2, right? -4 times 2 gives me -8. And -4 plus 2, right, gives me -2. Meaning, my top, I can now factor it to x minus 4 and x plus 2 all over x plus 2. Hey, what happens now? Yes, these two cancel out, right? I'm going to go ahead and rewrite my limit. And this is x minus 4. The limit is x minus 4. So I'm going to go ahead and apply my limit, right? I apply my limit. So this is -2 minus 4, meaning this is -6. Right? Again, what we did there was factoring. All right. Sometimes you may not have polynomials, right? Sometimes you may not have polynomials. You may notice, right? Again, right? I'm not going to assume anything. I'm going to go ahead and plug in 81. Okay, let me go ahead and apply the limit. I get square root of 81 minus 9. 81. I get 9 minus 9 over 81 minus 81. This is 0 over 0, meaning I have to do some work. Again, right? We're going to show our work. So now, whenever you're dealing with roots, right? Whenever you're dealing with square roots, and this is a hint, your square root may be in the bottom or it may be in the top. As long as you get 0 over 0, what you're going to apply here is you're going to take the conjugate of what has that root, right? And as a refresher, right, we said that if you have two numbers, all right, if you want to get the conjugate of those two values, it's going to be those same two values, but they just have, you just switch these signs in between them, right? Specifically, we saw this with complex numbers, right? You can get you can take the conjugate of complex numbers or roots. Meaning, I'm going to multiply the top by its conjugate, which is going to be the root of x plus 9. And I'm going to do the same thing at the bottom. Remember, whatever you do to the top, you have to do to the bottom. All right, so this is what I have here. Okay, this is what I have here. What I'm going to go ahead and do now is FOIL, right? I need to go ahead and do FOIL. So first, right, this is just going to give me the square root of x times 2 outside, inside, last. Right? Divided by first, outside, inside, last. What is minus 81 times 9, right? But it gives me that. All right. Let me go ahead and see what happens at the top, right? Well, what happens at the top? We know a squared with a square root cancel each other out, meaning I just have an x. You'll notice, right, from these conjugates, your middle values always cancel each other out. And the last value, I get negative 81. As a reminder, right, to make things easier before you distribute the bottom, I'll go ahead and give you all a hint, right? Because I forgot about this part. Leave your denominator like that. Go ahead and leave your denominator like that. All right. And the reason I want you to do that is because once you simplify the top, you're going to want to check if things cancel each other out. If they don't, then that's fine. For the time being, just go ahead and leave your denominator the way it is. Leave it the way it is. Right? It's the top that you really want to simplify. All right. And what happens? All right. What ends up happening? I end up getting, right, x minus 81 over x minus 81 times root x plus 9. Hey, what happens? These cancel out, right? And this is why I also didn't want to distribute right away, in case something did cancel out, right? And if it did cancel out, it's less work for me, right? If it didn't cancel out, then that's fine. Things simplified and things are still going to be easier, all right? So nothing is left on top, meaning that's just going to be a 1 over, wait, let me go ahead. We got to be very specific here. This is the limit as x approaches 81 of 1 over roots x plus 9. Okay, and what we said, right, once we either factor or take apply the conjugate to roots, right, with these, you plug in your limit. You try your limit again. So this is 1 over square root of 81 plus 9. Hey, no zeros over zeros. That's great. 1 over 9 plus 9. Hey, this is 1 over 18. That is awesome. All right. That is what my limit is approaching. Right, that is my limit. Right, and remember, whether that root, like this guy here, right, whether that is in the top or on the bottom, you apply your conjugate, right, to get rid of it. You apply your conjugate, and then you where that conjugate was applied, right, I distributed on the top, but not the bottom, to make sure if things cancel out, and vice versa, right? So keep an eye out for that, right? Okay, so you're asked to evaluate the limit of a square root. There's no denominator, right? So I'm going to find out what this is, right? I'm going to apply 4, but slightly to the right. So in other words, right, we said you can look at 4.1, or you can look at 4.1, right? So I'm going to go ahead and apply that limit. So this is 4 minus something slightly greater than 4. All right. So this ends up giving me, you have 4 minus something that's a little bit larger than 4. Is my overall sign going to be positive or negative? Right. And when we said, right, you can go ahead and do this. You can do 4 minus 4.1 because we're focused on the sign here, right? We're focused on the sign here. That's going to be a negative value. Right, a negative value, and it's going to be a very, 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 very small negative value. So I'm going to say this, right? Something very, very small, but slightly, it's negative, right? What do we know about square roots, right? What do we know about square roots? That in order for you to take the square root, the number must be 0 itself or greater. You cannot take the square roots of negative numbers because that's going to be complex numbers, right? And we're only dealing with real numbers. All right, meaning, hey, this is negative, right? So in other words, this is like saying the square root of negative 0.000001. It doesn't matter, it's still negative, right? So in other words, this doesn't exist. That right there does not exist. Right? If it was positive, that's fine, right? It would exist. All right, it was right, it was positive, it would exist. All right. So let's just say I had asked you the limits as x approaches, we'll say 4 from the right of x minus 4. All right, right? If you see here, order does matter. All right, so we'll say I'm going to go ahead and apply my limit, and this is 4 slightly larger minus 4. All right. So it's going to be 4.1 minus 4. It's going to be it's going to be 0, right? But it's going to be positive, right? It's going to be positive. It's going to be from the positive side. But hey, guess what? I can take the square root of 0 values, right? That's totally fine. What is the square root of 0? All right. So just keep an eye out for those, right? Keep an eye out for those. Right, I have another one here. Hey, this looks familiar. This looks very familiar, right? The limit is approaching 0 of sine of 5x over 9x. Man, all right. Okay, so I know I'm dealing with sine of 5x. This is very similar to that rule I mentioned in 2.2, right? And I know I can apply that rule here, that identity, because it's x is approaching 0, right? Didn't matter if it looked like this. We said, all right. Doesn't matter if it looked like this. It's just a variable, right? And the variable won't change anything. It can be r's in there, or l's, or z's, right? The same rules still apply. All right. So one thing we said is the number on the inside of the sign must be the same thing at the bottom and with an x. Okay. So I don't have, in other words, I need to have a 5x, right? It needs to be a 5x. It needs to be a 5x. There's already an x at the bottom, but in other words, it's missing a 5. I wish I had a 5 down there. All right, because then that'll make things even better. And we know that whatever I do to the bottom, I have to do to the top. Right, so in other words, I have the limit as x approaches 0 of, we'll say, 5 sine of 5x over 9 times 5x. All right, and 9 times x times 5 is the same thing as, right, if everything's multiplying one another, they always give me the same answer, right? So order of these wouldn't matter, right? 2 times 2 times 2 will always give me 8, right? 6 times 4 times 3, right, will always give me the same value. Doesn't matter if I start with a 6, the 2, or the 4, right? So here I have that, right? Well, let me go ahead and separate things, right? I want to go ahead and apply those limit laws. This is the sine of x equals to 0. We'll say 5 over 9 times sine of 5x over 5x. Right, this is just then the limit as x approaches 0 of 5 over 9. Go ahead and put some parentheses, right? Times the limit as x approaches 0 of sine of 5x over 5x. Hey, from that identity, we already know what this is, all right? This is 1. And we know that the limit, right, of a constant, right, it's just that constant itself. This is 5 over 9, right? And any number times 1 is going to be that one any number, right? It's going to be itself. So the answer for here would be 5/9, right? And for the last 2 problems, right, towards the end, you should have like 2. I'm thinking of adding 2 or 3, or maybe even 4. Right, you're still gonna have to play that. We're still gonna be playing that game, right? That sine game, all right, where you need to get right, the limit as x approaches 0 of sine of any number x divided by the same number x will always be 1, right? You may have to multiply the top and the bottom by something, right, to get it to that, to make it work for you, right? So it can be 1, right? So using still this identity, I'll give you 2 hints. I need you to remember your trig identities, all right? We're going to be using trig a lot in this class. So if you don't, please shoot me out an email. I'll go ahead and send you, you know what? And I think when it gets closer, I'll go ahead and post up a cheat sheet, right? I'll go ahead and post up this cheat sheet of the formulas we're supposed to know in case we forgot, right? But we are going to be using trig quite a lot in this class. But basic ones, right? Basic ideas like, all right, like that Pythagorean theorem, the reciprocal identities, and so forth. So just remember tangent, right? We know it's the same thing as sine over cosine. So remember that going in. If you see tangent, you can make that substitution. And one of my favorites, right, is if you have sine of squared of x, this just means, right? I always like to rewrite these, right? Because the placement of that 2 always throws, right? It used to throw me off, right? It would throw us off. So this is just the same thing as saying the sine of x to the second power, right? And if you have that, that's the same thing as saying sine of x times sine of x, right? You just have 2 of those, all right? That's all it means. Just like x squared, right? That just means you have 2 of those. So that is all I have for you today. Thank you very much, and I hope you enjoy the rest of your day. Thank you.